Good morning, ladies and gentlemen. I'm Arpit Jaiswal presenting with you portable hand gesture recognition system for generalized sign language. So first I'll let you know what this system is actually about. So basically what we are trying to achieve here is a hand-based system that could be used for gesture recognition. Why make it portable? So that it could be used in daily life for various activities by deaf and mute people. It will be easier to carry and lightweight. And what is gesture recognition? Well, we want to deduce meaningful inferences from a set of defined gestures. This could be a user customized gesture. It could be on American Sign Language. It could be on Indian Sign Language. Then why this is generalized sign language? Because as I said, it is user defined and you could customize it according to your need. And the system, as we have developed, the research we have put in, the idea was to present you with a system that is customizable by the user. So this is a short video that will introduce you to the idea of the concept and the people it affects. Right. So I hope you get a good idea about what the system is about and what we have trained it for. So the main crux of it is developing a hardware-based system, doing proper research on it for differentiating it with the current trend that is used in gesture recognition. And I will do a comparison for you between the current trend and the trend that we are following in the concept of gesture recognition. So currently, people are working on image-based gesture recognition. So in image-based gesture recognition, we have a dedicated system of camera wherein it has to be kept stable. There has to be ambient light conditions for it to work effectively. You're aware about various products based on it, like Kinect used by Microsoft, where it is used in playing video games, etc. But it couldn't be used for a system wherein a person is walking around in a market and wants to communicate with other person who doesn't know the sign language, or something similar to this, where portability is required. Whereas in our sensor-based gesture recognition approach, we don't require ambient light conditions. It is portable because it is wearable, and it doesn't require to be kept very stable. It will work in your everyday daily routine. So people are actually working on sensor-based gesture recognition, but how is it different? How our methodology is different from what people are actually doing? I'd like to give you some differences on that. So mostly work on this is done in US for American Sign Language. American Sign Language is one hand system. That is, you just have to do recognition on one of your hands. You don't need both your hands. Whereas Indian Sign Language requires both your hands. For example, if you make a A, in Indian Sign Language it has to be something like this. So to recognize both hand gestures simultaneously, you need to develop a system, and you have to develop a data set, train your machine learning models according to it. But before doing your research on that, you need to develop that system. So what we achieved with our methodology is we were able to get very high prediction accuracy because the kind of data set creation techniques we have researched over were very efficient. We were able to reduce latency by a very high amount, and we were able to achieve 5 gestures per second. And yes, the techniques that we have evolved were such that a user need not imitate the same gesture while training their module for a longer period. They can do it with just 5 to 6 repetitions and the model will be trained for that particular gesture. So this is our workflow, how we were able to develop the system before actually getting into the research phase, and this is how our presentation will also proceed. So we started with hardware design. We had to identify what all systems were needed to create this module, and we had to identify the kind of microcomputer will be needed if we will be able to achieve the kind of computation that is required for the system to work. And then we moved on to the validation of concept before moving on to having a validation of 2-hand system. We had to validate it if the concept is actually working for 1-hand system or not. And then we moved on to interfacing both hands. We needed fast communication between both hands. We wanted to reduce latency on multiple fronts. Then we moved on to improving readings from our inertial measurement unit, that is accelerometer and gyrometer. We used various filters like complementary filter, which actually gave us good results. Then we moved on to improving our dataset collection techniques, and then we moved on to something that is of the practical nature. Without it, it is of no use. That is improving latency issues, because we want more gestures to be recognized at a faster rate. That is, if a person is doing a particular sign, he need not wait for 2 to 3 seconds for a gesture to actually be recognized. It should be recognized instantaneously. And we put in efficient research in that phase also. Finally, we did heavy testing of it with actual people. And so yeah, moving on further, this is a major hardware design. So in our ideation phase, we needed to identify if this is actually possible, because people are not really working on this aspect, although this has many advantages. So we went on to identifying what are the modules or what are the processing things we will actually require for creating such a system. So we needed a computer that is small in size, it is portable, and has efficient computation backing to create a online training system that is working in real time. So we went on with Raspberry Pi. It's a smaller version of it, released 2 years back, and we then went on to identify the sensor inputs that will be needed for our system to work. So basically, whenever you want to recognize a gesture that is not happening in front of a camera system, you will want to place your hand in a 3D environment and need to see what its angular rotation is and what its movement is like. How is its angle variation changing? So for it, you will need an inertial measurement unit, that is the IMU, and an IMU consists of a 3-axis accelerometer and 3-axis gyrometer. So by using this, we are able to classify the rotation of our hand in a 3D system. Apart from that, we actually need to see what is the position of our fingers, how much bend is there in the fingers. So for that, we use flex sensors. Flex sensors give you a variation in reading depending upon the curvature bend in the flex sensor. So after identifying the system, we moved on to integrating it with the microcomputer. Then the sensing module was done with MPU6050 and flex sensors, and we wanted it to be user compatible. So we had a display module in the form of a mobile that the person is using, and you could get the gesture recognized output directly to the mobile itself. So this is the interface board that we have created, and you can see the Raspberry Pi hooked up to it, and the MPU6050. We did all the ADC, and we provided support for flex sensor connection to the board. So right now we are only at the ideation phase, and when we actually moved on to testing this concept, if this was actually achievable or not. So there were 4 phases involved with it. We had to collect sensor data, we have to create the data set, we had to classify using various ML algorithms. There are a bunch of it, and we had to choose what were best. That was a major core of our analysis, to see which kind of ML algorithms will do good with this kind of data set. And then we had to move on to real-time predictions to see if it performs good in the real system or not. So this was the first problem that we faced while developing this system. That was the problem of continuous gesture recognition. So let's say that you're doing a gesture that is a C and then a O. So of course, when you're doing such a gesture, you don't actually don't want to continuously output the results. You have some certain sampling points. So we needed that sampling point. Else you will be outputting some random unknown value when you are at rest, and you're outputting some logical value but in a repetitive sense whenever you're doing a gesture. So you'll be having this kind of output where you have unknown value, then you have continuous known values. So how do you deal with this? So we actually, as in the video you just saw, that the person who was performing the gestures was taking his hand down for the rest, then he was doing the gesture again. So we were able to establish a model based on that, that whenever you're making a gesture, you have to place your hand in a rest position before doing the next sign. So we had to validate this model. So the idea was that we won't record data when we are in the rest position. When we move to the gesture position, we will record data, and we will do online classification based on the system we have trained. So how do we actually achieve this? So when we are working with the accelerometer and we want to identify the rest position to gesture position transition, then we will see that when we move our hand from here to here, we are actually giving it a velocity, then we are reducing the velocity. So the trend with acceleration will be, it will be a positive acceleration. Then when as we are stopping the hand, it will be a negative acceleration. By identifying proper threshold, we can actually identify the state transition from rest to gesture position. Similarly, vice versa, we can do a gesture position to rest position interaction and identification by doing this negative to positive variation of acceleration. So this way we were able to achieve an output that was independent of continuous gesture recognition. So after we were able to tackle the problem of continuous gesture recognition, we did a preliminary testing and we were able to see outputs on one hand. So the next phase of our development was integrating both the hands, and that was the main thing because people were already working on one hand model. So to see actually if the ML algorithms work on two hand data sets accurately and fastly, we needed to first integrate the two hands. So that involved achieving communication with the two hands wirelessly. That is, we don't want any wires to be connected, and we want it to be a portable system. And secondly, we want them to be in sync. That is, if one hand is recognizing or collecting some data, then the other hand should also collect the data at the same time and not independently of each other. So solving the first problem of achieving communication, we already use the established protocols of SSH and MPI4PY. So MPI4PY is a distributed parallel computing library, and our system is a two-hand based system, and it has two microcomputers on each the hand, and we want the data to be exchanged at a faster rate and in the form of small packets. So this combination provided us with the security and the data exchange capability for the system to work. Then we moved on to our second problem, that was synchronization of the hands. So how did we find that this is actually an issue? Because let's say you are doing continuous gestures and you have this kind of algorithm moving in both of your hand, where you have motion detection recording data, then one of them is sending data to the other hand, which is concatenating the data and predicting the output based on that data. So in this phase, when you are detecting motion independently on both your hands, it could be easily seen that your hands could be out of sync, because mostly people are right-handed or left-handed. So if a person who is right-handed will have good control over his right hand, and he might be able to easily cross the thresholds with the right hand, but not with the left hand. So it might be unaware to the user, but his left hand might not be able to share the data with the right hand, and there could be multiple and lots of issues and complexities with that. So we provided an innovative approach to this, and we moved the motion detection part to the user's active hand, that is the right hand in this case, and only this hand will detect the motion and will share that I have detected the motion to the other hand, and using the sync pulse, both of them will start recording data at the same time, and this will deal the problem of synchronizing both the hands. Now, as I was saying that we needed sensors to collect data for the ML model to work. So MPU 6050 is an accumulation of gyroscope and accelerometer. Both are 3-axis devices, that is, they will give you readings in X, Y, and Z directions. So accelerometer is noisy in short term, but the data accumulation improves over time and it gives you accurate acceleration changes over time. Whereas the gyroscope is accurate in short term, but it drifts over time because it has an integral effect. So we used Kalman filter. A lot of research has been done on it, and it has been found that Kalman filter accurately combines this and gives you improved results. And from this result, you can actually calculate angles. We have 3 angles: raw, pitch, yaw, pitch, and roll. And we actually needed roll and pitch for the classification of our data. So, but there's an issue that Kalman filter is very computationally expensive, and a microcomputer that is already doing lots of tasks like communicating, recognizing sensor data, and apart from that it has to do Kalman filter implementation, then it will be very complex and might not be achievable. So we moved on to complementary filter, which is a simpler and easier system for Kalman filter, and this is a general idea behind the complementary filter, where you assign weights to the angle that you calculate from gyroscope and accelerometer. From our testing, we found that we have to give major weight to gyroscope angle because it is more accurate in shorter period, and this helps us achieve accurate readings and angles. So after achieving improved readings in MPU 6050, we were able to offload our complementary filter calculations to the digital motion processor in the MPU 6050, saving us more of that time. So how do you move on to creating a data set? So in our system, we actually aim to implement an online system. That is, we wanted to let a user do a sign, then identify what sign he was able to do. And to create a data set for that, we have to have a creation technique which replicates the actual scenario. So what we did was we handed over the system and hooked it up to a person, and he had to do a gesture, perform the 2 hand gesture simultaneously. Say this is a A gesture, this is a D gesture. He will perform that. We will consolidate the data in a form of a tabular form in an Excel file, as you were able to see in the video, and then we will ask the user to repeat it for 5 to 6 times. Then we will train the model, and we will analyze the results. So this was our data set creation technique. So a very big problem that we identified by going through the data set was that the angular variation that we were getting was not very good, because some of the gestures that we are performing would have a 90-degree variation, that we are doing a C, that is having a 90-degree rotation, whereas a M is more like 40-degree, 45-degree. And while we were performing that C gesture, we noted that the data set that was created has faulty readings because the variation was only 30 to 40 degrees instead of 90 degrees. And we moved on to improving the data set collection by changing the weight parameter of the alpha in the complementary filter, and we fine tuned it, and we were able to achieve good readings for the problem. Now for the actual practical system to work, there are various latencies involved, and to discuss them, there is a recording data latency, there is a communication and synchronization latency between both the gloves, and then there is a prediction latency, because every ML algorithm has its own calculation and complexity timing, and we wanted the system to be as fast as possible. So one of our research goals was to analyze all the ML models to see what are their latency results. So we did, first of all, we did the accuracy analysis with this is the training set, and we had 40 odd people performing 26 gestures in Indian Sign Language, and we found that KNN and logistic regression, SVM and kernel SVM were giving very good accuracies. KNN was actually giving close to 95% in its results, and logistic regression was also good, but it was not able to differentiate between some of the common signs like C and U, which are very similar to each other, and KNN was able to differentiate them very nicely. Then we did timing analysis, and in timing analysis we found that KNN was a little bit slower. It was taking about 500 milliseconds for it to recognize one of the signs, whereas logistic regression was way faster. It was doing it in 1/5 of that time, and we were able to recognize up to 5 signs per second with logistic regression based model. And but ultimately it turned out that KNN is sufficient for a person who is performing these signs in online mode, because he won't be able to perform 5 gestures per second. and we are getting very good accuracies with KNN, so it's 5-star needs. Then we moved on to the test set where we actually had 230 people perform different signs, and we found that KNN turned out to be pretty good, and it was almost 92% more than it. And logistic regression was also good. That gave us the idea that if we further proceed our research with forms of neural networks like recurrent neural network, which is based on time, we could get better results with logistic regression. And yeah, this is our analysis. So there's lots of future work. We have only explored one of the regions of and the possibilities of such a system, and that was recognition of sign language. And there are various many more possibilities, and there are various many more improvements that could be done in the system. Like we can work on reducing the form factor of the hardware. We can implement neural network because it seems to be a very good approach, because logistic regression gives very good results. And we can move on to, so currently we are doing static gesture recognition. That is, we are not doing something like this is hi, how are you. So which will require dynamic gesture recognition, and we can move on to DTW, that is dynamic time wrapping kind of algorithms. Right. So that's it from my side. Thank you. We are open for questions.